This is fundamental problem 6 from chapter 16. For a short period of time, the motor turns gear A with a constant angular acceleration of 4.5 radians per second squared starting from rest. Determine the velocity of the cylinder and the distance it travels in 3 seconds. The cord is wrapped around pulley D, which is rigidly attached to gear B. I'm looking for the velocity of cylinder C. I'm given the acceleration, the angular acceleration of gear A, so I have to use that to find the velocity of cylinder C. I'm going to start off by finding the velocity of, the acceleration of cylinder C, and then use that to find the velocity. They're calling this point P here. This is on the rim of gear A and also on the rim of gear B. If you look at point P, you can write an expression for the acceleration of this point using the angular acceleration that they give you here. This is what we saw a few pages ago on page 325. So you can use this to find the tangential component, and you can use this equation to find the normal component. If you look at a tooth for gear A and a tooth for gear B, at this point here, those teeth must have the same tangential acceleration because the gears are meshed here. Those teeth are moving together. The normal component of the acceleration may be different, but the tangential component for the acceleration will be the same. So we can use what they gave us for the tangential component of the acceleration. First, we're going to find the acceleration of cylinder C. I'm going to start off by saying that equation that we just saw, that was for the tangential component of the acceleration. That tangential component of the acceleration is angular acceleration crossed with r. Those vectors are perpendicular to each other. So I have the tangential component of the acceleration at point P is equal to the angular acceleration of A times the vector r that would have a magnitude of RA. But I can also write the tangential acceleration of point B using gear B. And that would be the angular acceleration of gear B times RB, which is the distance from here to that point. So this is the tangential component of the acceleration at a point on the rim of gear A and also on the rim of gear B. I can rewrite this as angular acceleration of B is equal to angular acceleration of A times RA over RB. And I want to use that to find the acceleration of the cylinder. Well, gear B and gear D are rotating together, so they must have the same angular acceleration. So the angular acceleration of D is equal to the angular acceleration of B since they're rotating together. So the angular acceleration of D is equal to the angular acceleration of A times RA over RB. Now if I look at point P prime, if I look at the tangential component of the acceleration here, that must be the same as the acceleration of point C. So using the same formula that I used to get this here, the acceleration of C is the same as the tangential component of the acceleration at point P prime. Using the acceleration of D to get that, that would be the angular acceleration of D times this distance from here to here, that's RD. But the angular acceleration of D is angular acceleration of A times RA over RB, and this is times RD. So all of that will give me the angular acceleration of point C. So now, hopefully all of this was given to me. So angular acceleration of A is 4.5 radians per second squared. RA is 75 millimeters. Our B is 225 millimeters, so this is 75 millimeters divided by 225 millimeters. Those units cancel out. Our D is 125 millimeters, but let's convert that to meters and call it 0.25 meters, 0.125 meters. And if I don't want the units of radians, I can just cross them out. So this will give me the acceleration in meters per second squared. This is 0.1875 meters per second squared. And if the angular acceleration of A is this way, then point P must be going this way. So the angular acceleration of B would be going this way, which means the angular acceleration of D would be going this way. And over here it would be going up. So the angular acceleration of C is pointed upward. I was asked to find the velocity of the cylinder after 3 seconds. Well, in the problem that they told me that this angular acceleration was constant, so that means the angular acceleration of the cylinder is also constant. So I can use one of the equations from chapter 12, or I can draw a graph of velocity versus time. And somewhere I was told that I was starting from rest. So the initial velocity is 0. The acceleration is the slope of the velocity versus time graph. So the slope is equal to the acceleration of 0.1875. We want to find the velocity at 3 seconds. That would be this velocity here. We also want to find the distance. The distance is the area underneath the curve. And the velocity is what I have here. So I can say the distance is the area of this triangle here. That is, since it's a triangle, 1/2. The base is 3 seconds. And the height is the velocity, which I didn't find yet. What do I want to call that? How about VC2? I can look at the slope, and the slope, 0.1875 meters per second squared, is equal to the change in velocity over the change in time. The change in velocity is VC2 minus 0, since we started at 0, divided by 3 seconds. So my velocity is 0.1875 meters per second squared times 3 seconds. And that is 0.5625 meters per second. Since the acceleration was pointed upward, the velocity is pointed in the same direction as the acceleration. So this is also pointing upward. And then I can take this and put it in here. And the distance that the cylinder travels is 1.5 seconds times my velocity of 0.5625 meters per second. And that gives me a distance of 0.844 meters. So I have the distance that the cylinder travels and the velocity. And that concludes Fundamental Problem 6.